I'm going to do another outline, just go through everything that we've done, organized a little bit differently. I don't know, I hope that sort of the slight different focuses or grouping things differently kind of makes your brain activate or whatever. I feel like it helps for me, so that's why I'm sort of doing it a little differently every time.
The changing of the status exam date, exam date is not going to change it next Monday. Right?
That's right. Yeah. So yeah, let's go through that first, I guess. Yes. What? Oh, yeah. Yeah, it's it's scheduled for Friday, 12:15 at 11. That's really bad for the people who are also in statics. So I'm happy to choose other times for people taking both of them, because you'd be taking both of those back to back. So just talk to me, and I'm happy to make arrangements. But yeah, so Friday at 11. I might as well just check to make sure, but. Okay, so this is Monday, Wednesday, Friday at 10 a.m. So yes, Friday, 12:15 from 11 to 1. You won't need the full 3 hours. You can have 2 hours to do it, but. All right, so I'm gonna do kind of like a just linear outline of topics. I moved a couple things in the different sections or whatever, but I want to start by just talking about two things that come up a lot. The first one is cycles. So if you're given that something is a cycle, all properties have a delta of 0. Okay, so if you have a property Q, this is equal to 0. So that's true for mass in a control volume. If it's a cycle, it's true for entropy, enthalpy, any properties that you can look up in a table. Similar is steady state. So if something's in steady state, it meets this same requirement for a cycle. It's like a stronger thing than a cycle. So the delta Q is equal to 0 still. And also the time derivative of that property is always equal to 0. So we use that with dm dt. We use it for dE dt. Anytime you're taking a time derivative of a property and you're in steady state, it's equal to 0. Okay? So here's an outline of topics. I'm going to start by talking about simple compressible substances. How many substances have we talked about in this class that aren't simple compressible substances? Right. This is everything that we're talking about. And all of them, you can use a PVT surface to figure out, how those properties change in relation to each other. it's not really too useful to use the three-dimensional PVT surface. It's just hard to visualize. It would be kind of cool if you had a 3D one. I was thinking of trying to find numbers so I could make something like that in the 3D printer. That would actually be pretty cool. But for our purposes, what really matters is the vapor dome. So let's think of a temperature versus volume curve. You have a similar thing if you have a pressure versus volume curve. You have a similar thing in a temperature entropy diagram. So we get a lot of different, slightly different looks to this vapor dome, but over here is compressed liquid. Over here is saturated liquid. In the middle is a mix. Over here is saturated vapor. If you're outside of the vapor dome on the right, this is a superheated vapor. At the top here, this is called the critical point. And this line here is the triple line. That's where all three phases are in equilibrium. Nope. I can't visualize it really. I don't know. Maybe there are YouTube videos that give you a sense of what's going on, but when you have pressures and temperatures above that, there's no longer any distinction between vapor and liquid. All you have is what's called a supercritical fluid. It doesn't change phases anymore. It's just this thing that'll burn you really badly. I mean, I suppose that's, there's probably substances where that's a low temperature, to be honest, you know, but yeah, that's what a critical point is, but I don't really have any other inside information on what that's like. Sometimes in Rankine cycles in power plants and stuff, you know, you get more efficiency the higher the temperature and pressure is. And so people will actually crank the temperature and pressure all the way up past that critical point. And so you'll have turbines that are where you're passing supercritical fluids through the turbine. But my understanding is that like liquid is hard on turbine blades. Okay, so what about phase change? If you think of this vapor dome and you're looking at temperature versus volume again, a constant pressure line through the phase change looks like this. This would be like relatively a high constant pressure. And this would be a low constant pressure. But the key thing about this is that you can see while the substance is changing phases at constant pressure, that temperature is constant the whole time. Okay, and that brings up the idea of latent heat. And latent heat is something that we want to take advantage of in engineering applications all the time. There is energy stored in a vapor, let's say a saturated vapor. That doesn't show up in the temperature. That's the latent part of it. And so this is also, it's a lot of energy. And so the nice thing about taking advantage of that is if you're trying to put energy into, if you're trying to put heat, say, into a saturated liquid, into any substance, I guess, it's easier to do it if that temperature isn't rising the whole time you're doing it. If you have a boiler that's 500 degrees Fahrenheit and you're putting heat into a gas, the temperature of the gas is rising, and the whole time the temperature is rising, it's slowing down how fast the heat transfers into the gas. Okay, and eventually the gas gets close to 500, and then it doesn't, no more is going to transfer. But if you have something that's 500 degrees, and then you have a saturated liquid where the saturation temperature at that pressure is 300 degrees, now you can pour all that heat into the gas, and it's storing that gas as latent heat, but the temperature of the mixture isn't going up. And so it's a much more efficient way to store energy and release energy. So that's a key thing in engineering applications. We talked about property tables a lot. We use property tables a lot. When a substance is at saturation, you only need one property. That's not how you spell property. When a substance is not at saturation, you need two. For 1D linear interpolation, you can always use this if you're at saturation. Then say that the properties that you know are a P1, a P in between P1 and P2, and a P2. And you also know a Q1 that corresponds to this one, and a Q2, and you want the Q value corresponding to that P. Then that Q is equal to Q1 plus the quantity Q2 minus Q1 divided by P2 minus P1. I'm using this P for property, not for pressure, by the way. It can be anything. Times P minus P1. So I don't know, I've written this a few different ways in function notation and whatever, but this is the way to find one property that you don't know. And then we did 2D saturation. So let's say that you know properties x1, x, and x2. And you know properties y1, y, and y2. And you know properties q1 and q2, but you want q at x, y. Then you can, in the xy plane, you have x1, y1, x1, y2, x2, y1, and x2, y2. And you have this location here, xy. Okay. Then we want to know what's q at this point here. Well, we do this in 3 steps. We'll say q at x, y1 is q at x1, y1 plus the quantity q at x2, y1 minus q at x1, y1 divided by x2 minus x1 times x minus x1. And then the second step, we'll calculate q at x, y2 as q at x1, y2 plus q at x2, no, q2. So we got q, yeah, right. So x2, y2 minus q at x1, y2 divided by x2 minus x1 times x minus x1. And then finally, we'll do it with the y. So q at x, y is equal to q of x, y1 plus q of x, y2 minus q of x y1 divided by y2 minus y1 times y minus y1. I haven't made you do this on a test in a long time, and I'm not going to in either of the next two, you know. And then the last thing, so this is 2D. This shouldn't say saturation, this should say interpolation. The last thing is quality. And the quality is defined as the mass in the vapor state divided by the total mass. And for any property, Q is equal to X times that property for the gas plus 1 minus X times that property for the liquid. Oh, that wasn't the last thing. There's a few more here. So we're still just going through kind of definitions for simple compressible substances. So now let's define enthalpy. The extensive enthalpy, H, is equal to the extensive internal energy plus the pressure times the extensive volume. And what we use more is the specific enthalpy, and that's the specific internal energy plus P specific volume. Then specific heats. It's worth keeping in the back of your mind that the specific heats have kind of this complicated partial derivative meaning, but remember, we don't use those at all in our calculations. So C sub V, the volume specific heat, is the partial derivative of U with respect to temperature, holding the volume constant. And the pressure specific heat is the partial of specific enthalpy with respect to temperature for holding pressure constant. If you get into more complicated heat transfer classes, you'll use these, but not in this class. And then incompressible materials. So these are the last two things. The first one is incompressible materials. And all the things that you know if you have incompressible materials, these are liquids. And sometimes you'll use this with solids. We use the incompressible assumption for solids. For example, when we talked about throwing a hot piece of metal into a water bath, you know, the calculations we did used the assumption of incompressible materials. Okay, so here are the things that you always know for incompressible materials. Specific volume is a constant. To be the most accurate, what you should do is look it up for the temperature that you have, and then use that as a constant through your whole calculation, because it fluctuates a little, but it doesn't fluctuate very much. Specific internal energy is just a function of temperature. Those specific heats are equal to each other, and we'll just call it C, and that's something you can look up in a table. And then based on that, the change in specific internal energy for an incompressible material is C times the change in temperature. And the change in specific entropy is C times the natural log of T2 over T1. So this is the stuff that, any of those that help you if you are treating something, if you're dealing with a liquid, you can use all those, okay? Seven is ideal gases. And the things that you can always use there. Well, in this case, I'm saying you can always use these, but I do have one part of it broken down into, okay, is there a huge temperature range or a relatively small temperature range? The first thing is the ideal gas law. PV equals RT. The specific internal energy is a function only of temperature. The specific enthalpy is also a function only of temperature. And you can figure out what that is in relation to the internal energy, because by the definition of specific enthalpy, it's U plus PV. PV is equal to RT. So this is equal to U plus RT. With similar reasoning, now for ideal gases, you don't have a single specific heat. You do have separate CV and CP, but CP is always equal to CV plus R. Okay, so now if you have small changes in temperature, the change in specific internal energy is CV times delta T. This is for relatively small delta T, but we've seen that, I mean, you can get pretty good values even if it's changes of hundreds of degrees Celsius. The change in specific entropy is Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. Do you remember how we derived that one? I think it's probably a good guess if, like, where do we derive anything? The best involving entropy, I should say. Anything involving entropy that we derive pretty much comes from the TDS equations. I haven't talked about that in this yet, but and then if you have a large change in temperature, then the change in specific entropy is equal to S super zero of T2 minus S0 temperature 1 minus R times the natural log of P2 over P1. This is more accurate if you have a large change in temperature. And where do you get those S super zeros? Do you remember that?
Yeah, you just in there.
Yeah, in the ideal gas tables. Okay, so these are like kind of all the things that you'd kind of like to always be at your fingertips for basically any substance, for any simple compressible substance. What are substances that aren't simple compressible substances? I think like long, really especially big molecules that flow like with a lot of viscosity, like oils or whatever, you can't use these calculations for stuff like that. What number are we on? Okay, so now this is a small one, but the second major section is conservation of mass or mass balance equations. And mass balance equations really are only useful for control volumes. So first, you have an equation that says the change in the mass inside the control volume is equal to the mass that's traveled in the inlet minus the mass coming out at the exit. This equation is for a finite time interval. If you're dealing with a cycle, this changes to the change of mass in the control volume is equal to 0. And so the mass that came in the inlet is equal to the mass that left the exit. And you can just think of that as, no, don't think of it like this. Just think of it like this. Second is the differential form. We use this one more often. The derivative of the mass in the control volume with respect to time is equal to the mass flow rate coming in at the inlet minus the mass flow rate leaving at the exit. This is the differential form. And by far the most common way that we use this equation is that if the process is a steady state process, then the mass flow rate at the inlet is equal to the mass flow rate at the exit, and you can just call that m dot. So mostly, we did a few conservation of mass problems, but by far the most common way we use this is just in modifying the first law for control volumes. Okay, so this is where it comes from when you say, okay, it's in steady state, cross out the m sub I dot, cross out the m sub e dot, and just replace it with m dot. We also did some things with this, remember, so if you start with this differential form, you can integrate it through time and figure out, so if it's not steady state, how long is it going to take to get us to a certain level of mass inside the device or whatever, if the inlet is doing this and the exit is doing this. Okay, so finally we get to the first law. And this is conservation of energy. The first way we saw this was the change in total energy is equal to the energy added through heat minus the energy output through work. This is over a finite amount of time. We often made the simplification that the change in energy is just equal to the change in internal energy. So we ignored what's happening with kinetic energy and what's happening with potential energy. If you're ever stuck on a test or something and this would fix your problem, feel free to assume that, you know what I mean? Unless, I mean, probably that's what I'm expecting you to do if I haven't said anything specific about speeds or heights or anything like that. One really important thing to use with this finite form of conservation of energy is the work of expansion. So that's the integral of PDV. What do you need in order to compute this? You either need pressure as a function of volume or just constant pressure. So what are some of the cases where we were able to compute this integral? Do you remember? What kind of things are coming up in the problem when we can compute it? For sure, if there's constant pressure, you probably want that to trigger you to say, you know, calculating that integral shouldn't be hard, you know. Alex, were you going to say something?
No, I'm stretching.
Oh, okay. Well, the other thing was when we had problems like P times V to the 1.3 power is equal to a constant. That kind of stuff lets you calculate P as a function of volume, and then you can do it.
You forget all your integration rules. That's it.
Yeah, right. Yes?
In the conservation of energy equation, T and V, which one's potential?
Oh, this is kinetic, and this is potential. People use all sorts of different notations for that, though. So it can be confusing because that also is a speed, and speed relates to kinetic energy, but and then we also use the differential form of the first law that says dE dt is equal to Q dot minus W dot. And again, often we're just gonna say dE dt is equal to du dt. Remember though that's, so what you get out of the table is the specific internal energy. So be sure if you're using this form that you're multiplying by the mass to get the extensive internal energy.
Yeah.
Okay. Okay, so what's this? This is for a closed system. And this is the differential form. We're also going to see a differential form for control volumes. The main thing we did with this form was use heat transfer equations. And the only thing you need to remember about using the heat transfer equations is don't trust the signs. You have to come up with the signs on your own based on what makes sense with your sign convention. So first we had conduction. And that said Q dot is equal to, well, there's a negative on it. I'm not going to take the negative off because that's the way you see this form. But remember that that negative isn't useful to you, you know. So just ignore that. But it's equal to the coefficient of conduction. That's that kappa. Thermal conductivity, I guess it's called, times the area of the window that it's traveling through, times the gradient dt dx. And for us, we're pretty much always just going to think of this as the change in temperature over the length that it's traveling. We'll just think of that as linear. Again, you won't do that if you take more complicated heat transfer classes, but. And then the second one is radiation. Oh, what were I meant to bring it up when I came to the things that people made a lot of mistakes on in the quiz. Most people got this one right, but radiation is the one heat transfer mode where it can travel through empty space. And there are two things we have. The first one is totally universal, but not very useful. The rate of heat emitted is the emissivity times the Stefan-Boltzmann constant times the surface area of the object times the temperature of the body to the fourth. The only one that's really useful to us is the net heat emitted, and that looks very similar. But it only works if you have a smaller body totally surrounded by a larger body. So you have emissivity, Stefan-Boltzmann constant, surface area of the smaller body times the temperature of the smaller body to the fourth minus the temperature of the surroundings to the fourth. This is the only one you can use in the first law. And then the last one is convection. And the rate of heat through convection is this catch-all thing that you look up experimentally, calculate experimentally, times the surface area that's exposed to the fluid. So that's not the total surface area, that's just the surface area that's exposed to fluid flow. Times the difference in temperatures, temperature of the body minus temperature of the fluid. When I said this, the only one you can use with the first law, I meant this is the only radiation equation, not the... Are you with me on that?
Yeah.
So this first one is a really important physics equation, but it isn't useful for our calculations, except that from it you derive that second one. Okay, and now finally we're on to everyone's favorite first law equation. dE dt for a control volume is equal to Q dot for the control volume minus W dot for the control volume plus mi dot times the quantity, hold on a sec. Times the quantity hi plus vi squared over 2 plus gzi minus me dot times the quantity he plus ve squared over 2 plus gze. And by far, the most often we use this, it's in steady state. So if you're in steady state, this reduces to 0 is equal to q dot minus w dot plus m dot times the quantity hi plus vi squared over 2 plus gzi minus m dot times he plus ve squared over 2 plus gze. Okay, and then a couple things that are useful with this equation over and over again. The first one is at either the inlet or the exit, m dot is equal to the area of the aperture times the speed divided by the specific volume. If the device is rigid and there's no electric power in or out, and there's no rotating shafts, then W dot is 0. Third, if it's insulated, so these ones in number 2, it's all these have to be met for there to be no work. If it's insulated though, or, so if any of these are met, it's moving quickly through the device, or it's a small surface area, then there's no heat transfer. Again, just like before, we often ignore the change in kinetic energy and the change in potential energy. Not always, but look for that as a possibility. And then the last thing for today is, what did we use this for? Well, we talked about, I'm not going to give you equations for these, because like on a test, I would want you to derive these based on what I say about the device. But we did nozzles and diffusers, turbines, and pumps and compressors. Anybody have any questions about anything I talked about today? So that's the end of the first law. And so next time I'll start with the second law, and then we'll get into Rankine cycle.